Okay, here we go. We're gonna do Unit 8 exam. You can write notes or you can just follow along. Again, this thing is being recorded, so you're gonna be able to watch this again and again if you want before the final. So let's just break it down really quickly, okay? So number one, if you look at number one here, it says sodium metal. So sodium metal and water react to form sodium hydroxide and hydrogen gas. Notice something that, when they say hydrogen gas, kind of like what I talked about, right? Hanaf-Kobri. These elements, Hanaf-Kobri, one second. So, what's special about these 7? Right? They're all found with the 2, okay? Always found with the 2. So even when they say hydrogen gas, let's say I don't give you this, you have to remember that it's H with a 2, okay? So this is the equation. It looks like it's balanced. I see coefficients. What did they give us here? They gave me 15 grams of this produced, and they want to know mass of this, okay? How you have to do this is grams is not good. You have to change it to moles. And then what you need to do is ride the mole ratio train. I know you're starting at the end. They gave you how much product you made, but you can ride the mole ratio train. Once you're in moles, you can ride the train anywhere you need to go. And this time around, they give you the end product, and they want you to ride the train back up to the reactant side, the ingredients. So once you change 15 grams to moles, you ride the mole ratio train back over here to sodium and find moles of sodium and then go back to grams. Okay, this is the move, okay? Grams to moles, mole ratio train, and then back to grams. Simple as that. Right? So 15 grams, you gotta go 15 grams. You have to divide it by NaOH. Na on the side, I'll just do it here, is 23 plus, 16 plus 1. So we're looking at, what is that, 40? And again, if my molar mass is wrong, please let me know. So 15 divided by 40, and I'm getting something like 0.375 moles. This one's kind of nice because it's like a 2-to-2 ratio, right? So where you're going, I'm going to Na, and that's going to go on top. Where I came from, NaOH, that goes on the bottom, you're multiplying this, right? So you're multiplying by 1 to 1. So the moles here are not going to change. It's still 0.375 moles. Yeah, and then times 23, right? To go back to grams, you have to multiply by molar mass. And molar mass of Na. And Na is 23. So you multiply those two and you get 8.625. Answer C. Okay? Okay, so I'm going to move right along, right? Let me know if I'm going too fast, or again, you're going to have this video, okay? So you can pause it, while you're watching. So number 2, let's take a look at number 2. It says, I don't know if I want to, I'm not going to do all of them. I'm just going to kind of talk you through it. Like number 2, it says if the reaction given below. So what are we looking at? We have 12 moles of aluminum oxide. That's right here. Right? 12 moles here. How many moles of oxygen is produced? You're already in moles, so that's great. What do you have to do? You just have to travel over to the question mark, right? You're traveling to a 3, you came from a 2. And so that's 36 divided by 2. That looks like 18 moles. And that's it, right? They want to know moles. You're still in moles, okay? When you ride the mole ratio train, you're still in moles. Sometimes they want you to go to grams, but if they don't want grams, you just end right there, okay? 18 moles. And you have number 2. All right? Okay, number 3. Number 3, what they give you is they give you grams and grams of 2 things. This is a sure sign that you're looking at a limiting reactant problem. One of those things is going to run out first. One of the 2 are going to run out first. Whichever one runs out first is the limiting reactant. Oxygen? How do you know?
Because it's by H, right? It's by H, right? So it's still going to be way less than oxygen.
So the easiest way, I mean, there's many ways you can do this. You can compare the 2 reactants to each other and figure out which one's going to run out first by figuring out how much of the excess is left over or if there's going to be leftover. The other really easy way is to change both of the grams. You know how they give you 8 grams and 9 grams? Change both of them to moles. Then separately use ride the mole ratio train separately to the product. It doesn't matter which product. Well, this time there's only one product, it's water. Ride both of them to water, then change then whichever one's less, whichever one's a smaller number is the correct amount of water you can actually make. And it's also, if you backtrack, you find out from what reactant gave the least amount of water, that's going to be the limiting. So, you have 8 grams here, you have 9 grams here, and the question is how many grams, okay? That's not the question. They want you to choose from these things, like what's limiting. Again, so I change it to moles, which is going to be 4 moles. And then, because molar mass is 2, okay? Molar mass of H2 is 2. 4 moles, and then ride the train, which is 2 over 2, which is, again, 4 moles of H2O. Right? Now, separately, do the other one. 9 grams divided by, this is 2 waters, so it's 32 is the molar mass. Right? 0.28125 moles. And the ratio is 2 over 1 to get to water. There's a 2 in front of H2O, there's a 1 in, and multiply by 2, and you're ending up with 0.5625 moles of H2O. Which one is less? Right? This one's less, and it came from the 9 grams of oxygen, so oxygen is limiting. So I would think that just C is the answer here. How many moles of H2O actually was made? 0.5625. So D is wrong. You're not making 2 moles. 36 grams. Well, you got to change this to gram. You got to change this bottom number to grams if you want. 18.02 is like water. So you made actually around a little over 10 grams. You end up with 10.136 grams. That's how much you actually made of H2O. Okay. Let's take a look at number 4. Some of you got confused about this whole mole ratio train. When they asked you this, and I'll try not putting this on the final, but if it's there, what is the ratio of moles of oxygen used to moles of CO2 produced? That means I need oxygen's ratio to CO2 like that. Not like wherever you're going goes on top, wherever you came from goes on the bottom. This is oxygen to colon CO2. So it's 2 and 1 and 2. Oxygen is 1 to CO2 is 2. This being your answer, okay? I know you have to go 2 over 1 when you're trying to travel over there, but the answer is not 2 to 1. It's 1 to 2, okay? It's just oxygen to CO2. So whatever's in front of oxygen and whatever's in front of CO2, it's 1 to 2. Okay? All right, number 5. Let's take a look. We're looking at lead nitrate can be decomposed by heating. What is the percent yield? They want the percent yield of the decomposition reaction. You have 9.9 grams. And it's heated to give 5.5 grams. Now, what's crucial here is this 5.5 that they gave you, it's the amount that you actually created. Okay, percent yield is equal to the actual that you actually got in the experiment over theoretical, which is what you would get mathematically if you did the stoichiometry with a calculator. That's theoretical. Times 100. Right? Times 100. So this 5.5 is the actual. That's what you need to know. So you're not doing anything with the 5.5 except putting it in the percent yield equation. What you need to solve for is the theoretical. And once you solve for the theoretical, then you have it. Because you can just divide the two times 100 and you have percent yield. So how do you calculate theoretical? They gave you 9.9 grams, right? You have to change it to moles. Then ride the mole ratio train to PBO. And then go back to grams. Right? It's all about that. Grams to moles, ride the mole ratio train, go back to grams. So 9.9 divided by divided by, and you find PB 207.2 plus 14 times 2 plus 16 times 6. So I got 0.02989 moles. It's 2 to 2 ratio, so you're going to end up with the same amount of moles of PBO. And then multiply that by the molar mass of PBO, which is again 207.2. Is that right? P207.2 is PB, plus 16 for oxygen. And I got for grams, I got 6.67. That is in theory, if the world was 100% yield, if this thing yielded 100% and it's like a perfect reaction and you don't lose anything. You don't lose anything to the atmosphere. It doesn't burn off and disappear. You've done it perfectly in the lab. In theory, this is how much you should get. But they're saying that you only got 5.5. It's heated to give 5.5. So that's the theoretical. Okay, 5.5 divided by 6.67 times 100, 82 something, 82 some, 82%. What is your percent? Okay. All right, let's take a look at 6. Hydrogen gas can be produced by reacting aluminum with sulfuric acid. How many moles of sulfuric acid are needed to completely react with 15 moles of aluminum? So this is sulfuric acid. That's what they want in moles. And I have 15 moles of this. So all you have to do is find out moles of sulfuric acid. You just have to write the mole ratio train to sulfuric acid. It's 3/2, right? So 22.5. Okay. All right, number 7. This is methane. Let's take a look. Methane and hydrogen sulfide form when hydrogen reacts with carbon disulfide. Identify the excess reagent and calculate how much remains after 36 liters of H2 react with 12 liters CS2. When they say at STP, there's like a magic thing about 1 mole of any gas at STP is 22.4 liters. There's a lot of different ways you can solve this, but let's get to moles, right? Just so you're comfortable with the moles. The thing about this, you know how they give you 36 liters and 12 liters, and you know how you have to divide both of them by 22.4? These two numbers, you can actually keep 36 and 12. That's what's in the world of this whole stoichiometry. If they give you liters and they say it's at STP, you can keep liters and travel using mole ratio. You can. Because essentially you're just going to divide by 22.4, and then at the end you're going to multiply that 22.4 back in. So you're going to divide by 22.4, fine. If you want to get moles and moles, you can do it. Then use mole ratio train, that's fine. And then go back to liters. Well, essentially you've divided by 22.4 at one point, traveled using mole ratio, and then multiply by 22.4. So essentially you can stay in liters if you want and travel using mole ratio. Both ways work. So So let me show you that way, okay? So what I do is I grab 30, because you don't know which one's excess yet. You don't know which one's excess, you don't know which one's limiting. Let's grab the first 36 liters. And what I wanna do is do a mole ratio to the other reactant. This is gonna determine how much of that I need. So 36 divided by 4, I'm starting here and I'm going to just the second reactant. That's why it's 1 over 4. 1 over 4, right? 9, right? 36 divided by 4 is 9. 9 liters is what I need. What I need of CS2. Question is, do I have 9 liters of CS2? How many liters of CS2 do I have? Yeah, I have 12, right? So if you have 12 liters, you only need 9. How much are you going to have left over of CS2? 3, right? So you have 12, you only need 9. That's why I calculated 36 times 1 over 4. Is to find out how much of CS2 I need if I have 36 liters of H2. If I have 36 liters of H2, how much CS2 am I going to need to use all 36 liters? I need 9 liters. It's 4-to-1 ratio, right? So if I have 36 liters of H2, I need 9 liters of CS2. I have 12 liters though. So I have plenty of CS2. That's great. I found out that CS2 is excess. I found out that CS2 I have 12 of, I only need 9 of it. So I'm going to be left with 3 extra liters of CS2. And so the answer is A. Now, you could have used this if you want and changed the liters to moles and moles and then found out how much moles left over, then changed it back to liters, you would still end up with 3 liters of CS2. But this way is way faster. So again, if they give you liters and they tell you it's at STP, you can start using mole ratio right away. You don't have to change it to moles to ride mole ratio train. You can travel in liters as well. You could travel in liters as well. Okay, silver nitrate and aluminum chloride react with each other by exchanging anions. What mass in grams of AgCl, so they want, is produced when you have 4.22 grams of AgNO3 with 7.73 grams of AlCl3? So we're good, yeah? How would you go about doing this? All you have to do is change both of the grams, change them to mole and mole. Yeah, just do mole ratio to get moles here and moles here. Do them separately. Whichever one's less, whichever one has a smaller number, that is going to be how many, and then choose whichever one's smaller and then go back to grams. Whichever one's smaller. It's as simple as that. So you just have to carefully, I'm not going to do this one. You can do it. You can just say, all you have to do is change each of the grams to moles, then ride the mole ratio train. The mole ratio train is different for both, right? For the first one, it's going to be like this one is going to be 3 over 3. because there's a 3 here and a 3 here. The second one is going to be 3 over 1. So this is going to be 3 over 1. So they ride different mole ratio trains. Change them both to moles, ride them over to the right, whichever number is less, ride that one back to grams. And that would be your answer. Whichever one's less, whichever one creates less is the one that's important to figure out how much you can actually make of that product. This arrow here is a little misplaced. I guess you can, So change the grams to mole, then ride the two different trains over. Whichever one's smaller, whichever one is smaller, between these two, you ride that, you change that smaller number to grams by multiplying by molar mass of HECl. Okay? So as you're rewatching this video or whatever, and you pause it and then try to solve it, see if you can get one of these answers. Number 9 is balancing. They want to know what's here, right? They want to know what's in front of the O2. I feel like there could be a 10 here in front of the CO2 because of the 10 C's. It's all about the left side. You know how there's an arrow here? It's all about the left side versus the right side. They need to be equal each other. We have H2, maybe put a 6 here. And then you have to kind of figure out the oxygens. There's 20 oxygens here, and there's 6. That's 26 oxygens already. There's 4 here on the left. And I kind of have to make... I need to make this, 22, maybe 11 here, or no? Make it 10 CO2s, 6 H2O. Six. Oh, there's 2 more oxygens. That's 28. There's 4 here already. I need to make the second number be 24. So I'm looking at maybe a 12. And then I double check like several times just to see, okay, that is correct or not. Are we good with this one? There's 10 carbons, right? So what I did was I put a 10 here to make it 10 carbons. There's 12 hydrogens, so I put a 6 here to make it 12 hydrogens. Then oxygens, you have 20 oxygens here. You have 2 oxygens here. And you have 6 oxygens here. That's 28 total oxygens, okay? 28 total on the right. Over here on the left, I have 4 here already. So this by itself, because it's, left side versus the right side. the second slot here where it's O2, I need to make up to 28, so I got to make up to 24. And to make this 24, I have to put a 12 here. 12 times 2, 24. And they wanted that number. Okay. Okay, this one is a little tricky. They want H2O react with O2 and they made H2O. They didn't mention anything. They don't show you a formula, so this is kind of tricky, but they tell you everything that's made. What you have to do is you have to balance it. You have to make sure it's balanced. You need a 2 here and a 2 here. They tell you you have 0.40 moles and 0.15 moles. A problem like this can be kind of challenging, right? So how do you go about doing this? It says what mass of reactant remain. So you have to find out which one is limiting. Then what you need to do is you need to ride the mole ratio train from the limiting reactant to the excess, compare it to how much excess they gave you originally, subtract how much of the excess you're going to use to figure out how much excess you're going to have left over, and then change it to grams. So let's just figure out which one's limiting first, right? If you want, you can figure out which one's limiting by just going over here. So this one, you're going to be times 2 over 2, right? To write over here. This one, the 0.15 moles, you're going to multiply by 2 over 1 to write over. So I'm going to end up with 0.40 moles here and 0.30 moles here. Which one's less? This one's less. So O2 is limiting. Now what I need to do once I know what's limiting, this is what you need to do. This is the step. You have to ride the mole ratio train. This is the limiting. Ride the train to the excess. Ride it over to the excess. 2 over 1, which is 0.30 moles. This is crucial. What this 0.30 means is out of my 0.40, I'm going to use 0.30. Out of my 0.40, I'm going to use 0.30. So it's 0.40 minus 0.30. I have 0.10 left over. 0.10 mole left over. This is of H2. And then multiply it by the molar mass of H2, which is 2, to get 0.20 grams of H2 left over. That 2 is the molar mass of H2. Again, this problem, there's so many different ways you can do this problem too. You got to find the limiting. You got to find out the limiting, and then you got to find out if you have that much of the limiting, how much of the excess you're going to need to use. And subtract that from how much excess you actually have. That's how much of the excess you have left over. And then change it to grams. Okay? Okay, I want you to just try number 11 on your own. If you need, I can do it. Let's look at number 12. Okay, number 12 really quick. How many liters of O2? So we'll react with 8.7 grams of this. 8.7 grams. So this one, what should you do? You got to change it to moles, right? And then use the mole ratio train to go to moles, and then just go back to liters. And 1 mole of any gas, right, is 22.4 liters. And it says is at STP. So 8.7 divided by 12.01 times 2 plus 4-ish, right? I got 0.31. Something like this. And then the mole ratio train is 3/1. So times 3. That's 0.9315 moles. And then back to liters. How do you do, if mole is here, you want to put mole here. So 22.4 liters, so you're going to multiply by 22.4. And you get 20.8 liters. So change grams to moles, write the mole ratio train to O2, then multiply by 22.4 liters. $13.14. It's a lot of the same stuff, so I suggest you try it. I think this one also has the answer key. If not, let me know. I think it has the answer key, so you'll have the answers too. Let's take a look at this one real quick. Number 15. What volume of hydrogen will be produced at STP by the reaction of 67.3 grams of magnesium with excess water? I don't know. I don't think I need to do this one, okay? So grams, change it to moles, right? Write the mole ratio train to get moles here, and then just multiply by 22.4 liters for 1 mole to go back to liters. You're using this as a conversion factor, okay? Okay, just a couple more questions really quick. Let's just take a look at number 16. How many grams of NO2 are theoretically produced if we start with 1.20 moles here and 9.90 moles here? the two numbers they gave you, you just have to write both of them, mole ratio train separately. Just grab both of them. They give you mole and mole. Write the mole ratio train separately to NO2. And then whichever one's smaller, change it to grams. Right? So 1.20 moles. To ride the train, it's 6/1 here. The other one, 9.90. To ride that train, it's going to be 6/6. You end up with this. 1.20 times 6. 7.2. This is smaller, so change this to grams by multiplying by NO2. $331. Okay. Are we good? Okay, maybe I'll just do the last one. So question 20, this is only 20 question exam. Hydrogen gas is produced when zinc reacts with hydrochloric acid. If the percent yield is 85%, how many grams of zinc are needed to produce 112 liters of H2? If it's only 85% yield and you need to produce 112 liters, that's going to be the actual. You're actually needing a larger theoretical. And they're saying grams though, right? Grams of zinc. Add STP. So let's change this to moles first. This is 22.4 liters is 1 mole of any gas. So 112 divided by 22.4. 5 moles I'm going to produce, right? I need to produce 5 moles. Even though the thing is only 85% yield. So how many moles in theory do I need to grab, right? So it's 85% equals 5 moles over X times 100. Right, I'm gonna divide by 100 to both sides, multiply it by X to both sides, and then divide it under 5. $85 divided by that. 0.85. X equals 5.88 around 5.88 moles is what I need to create of H2. This is what was difficult about this problem. Then ride the train over to zinc. It's 1-to-1 ratio, so it's 5.88 moles. And then I have to go to grams of zinc, which is multiplied by the molar mass of zinc. $63.65.38. $384 grams. So this question was pretty difficult. They said how much grams of zinc you need in order to produce 112 liters of H2. That's how much you actually want to produce, even though this reaction is only 85% yield reaction. This reaction can only yield 85% ever. So if you need to get 112 liters, then you're going to have to grab more than that, because theoretically, you have to grab more than that. I changed the 112 liters to 5 moles, and I figured out that I need to, theoretically, I need 5.88 moles, because it's only going to yield 85% of 5.88, and that's going to give me the 5 moles I need. I'm trying to make 5 moles. I know this reaction is always 85%, so I need to actually act like I'm going to make 5.88, and so I need to start with 384 grams of zinc. I need to react 384 grams of zinc to make 5.88 moles of hydrogen, which will actually only yield 5 moles because this reaction is 85% percent yield. Okay, we're going to stop